Calculus class. Today we're going to learn topic 52, parametric curves. So first let's look at if you were to imagine a particle moving along some curve C, such as in this graph. So here's curve C and the particle is moving in the direction of the arrows. Is it possible to describe C by an equation in the form y equals f of x? No, because C fails the vertical line test, therefore C is not a function on the Cartesian plane. So basically this curve C is not a function, therefore we cannot write a typical function equation for it. However, the x and y coordinates of the particle are functions of time. So we can write x equals f of t and y equals g of t. By introducing this third variable t, we can determine a point, x comma y, that we can now plot in a coordinate plane. So this leads to a definition of parametric curves. If f and g are continuous functions of t on an interval from a to b, the set of ordered pairs f of t comma g of t is a parametric curve C. The equations x equals f of t and y equals g of t are parametric equations for C, and t is the parameter. The point p equals f of a comma g of a is called the initial point, so where we start, where the object starts on the curve C. The point q, f of b comma g of b, is called the terminal point, so where the point ends. And the direction in which the curve is traced for increasing values of the parameter is called the orientation of the curve. So, a little side note, the parameter t does not necessarily always represent time, and in fact we could use a letter other than t for the parameter. But in many applications of parametric curves, t does denote time, and therefore we can interpret x comma y equals f of t comma g of t as the position of a particle at time t. And here are some really pretty parametric curves after you graph the points f of t comma g of t. Alright, so now we're going to sketch parametric curves. Sketch the curve by using the parametric equations to plot points. Then indicate with an arrow the direction in which the curve is traced as t increases. So here's our example. X equals 2 cosine t and y equals t minus cosine t, where t is between 0 and 2 pi. So notice how x and y are both written in terms of t functions. So step 1 is to make a table of values for the interval of t. So I'm going to have my t values and then the x and y values according to that t value. All right, so I'm going to start with t equals 0, and then I'm going to choose t values between 0 and 2 pi that are probably the easiest for me to evaluate, which would be pi over 2, pi, 3 pi over 2, and 2 pi. So now I'm going to go ahead and plug in each t value into x and y functions for t. So when I plug 0 in for 2 cosine t, I get 2. When I plug 0 in for t minus cosine t, I get negative 1. And then I keep doing that. So then I plug in pi over 2 to get 0 and pi over 2. I plug in pi to get negative 2 and pi plus 1. I plug in 3 pi over 2 to get 0 and 3 pi over 2. And then I plug in 2 pi to get 2 and 2 pi minus 1. Now for step 2, you are going to plot the x comma y points on the Cartesian grid. So like we normally do. So you're going to plot 2 comma negative 1 and so on. Then you're going to draw arrows that represent the direction a particle would be traveling on the curve as t increases. So And it would probably be easiest for you to plot these points if you translated these into decimals, which is totally fine. So after plotting each x comma y point, I get a curve that looks like this. Now I'm going to identify my initial point and my terminal point. So my initial point is my start, t equals 0, which is the point 2 comma negative 1. My end point is when t equals 2 pi, which is at the point 2 comma 2 pi minus 1. Then I'm going to indicate the direction the particle is moving. So if the particle starts down here and ends up here, that means the direction that my particle is going is following these arrows. All right, why don't you go ahead and try this example on your own. All right, let's see how we did. All right, I'm going to go ahead and plug in 0 for t for both x and y to get 1 comma 0. Then we do it for pi over 2 to get 0 comma 1. For pi, I get negative 1 comma 0. 3 pi over 2, I get 0 comma negative 1. And 2 pi, I get 1 comma 0. Now I'm going to go ahead and plot each of these points on my Cartesian grid to give me a lovely circle of a radius 1. And you should have that your starting point or your initial point is t equals 0 at 1 comma 1. And if you notice that your ending point is at the same point, which is t equals 2 pi, also 1 comma 1, or sorry, 1 comma 0. And then I'm indicating the direction in which the particle is moving, and it's moving counterclockwise around this circle. And if you noticed, it's the unit circle. So just a couple notes. The parameter t can be interpreted as the angle in radians in this example. And if the endpoints of the curve are the same, the curve is called closed. All right, so let's look at eliminating the parameter. So eliminating the parameter is a process that allows you to write the parametric equation in rectangular form. So going from functions in terms of t to our typical single function in terms of y equals f of x. So let's look at our first example. You're given that x equals t squared minus 4 and y equals t over 2. So you're going to start with the parametric equations, which we have. Then you're going to solve for t in one of the equations. It typically does not matter which one, but I would recommend that you choose one that's the easiest to solve for t. And in this case, it would be the y equals t over 2. So if I solved for t here, I get that t equals 2y. For step 3, you're going to substitute into the other equation. So for the x equals t squared minus 4, I'm going to put the 2y in place of t. All right, and in step 4, you're going to simplify, and the result is in the rectangular equation. So I'm going to go ahead and square the 2y to get 4y squared. Now, you don't have to solve for y unless you want to or you have to, such as like in a multiple choice question. You have all your choices as, of course, y equals. So go ahead and try this example on your own. In this case, it's not in terms of t, it's in terms of theta. So in this case, you'll solve for theta in one of them. So if I was to rearrange these, I would get that cosine theta equals x over 3 and sine theta equals y over 4. And I know that cosine squared theta plus sine squared theta equals 1. So when I substitute the cosine theta and sine theta in, I get x over 3 squared plus y over 4 squared equals 1. And I can reduce that to x squared over 9 plus y squared over 16 equals 1. All right. So for each of the following, I want you to first pause the video after I explain the directions and try this on your own. But for each of the following, you are going to sketch the parametric curve and indicate with arrows the direction in which the curve is traced as t increases. Then you're going to eliminate the parameter to find a Cartesian equation of the curve. So go ahead and pause the video and try them on your own. All right, let's see how we did. All right, for the first one, we have x equals t plus 1, y equals 5 minus 2t, and you're going between -2 and 3 for t. So I'm going to set up my equation or my table, pick values that are within the interval that would be easy to plug in, plug those values in to get the points -1, 9, 0, 7, 1, 5, 2, 3, 3, 1, and 4, -1. Then go ahead and plot the curve and indicate the arrows in which the particle is moving. Now go ahead and we're going to solve for t in one of these equations, and it makes sense to solve for t in x equals t plus 1. So t equals x minus 1. Plug that into the other one and simplify. So you get y equals -2x plus 7. For the second one, we have that x equals natural log of t and y equals the square root of t, where t is greater than or equal to 1. So in this case, I'm going to pick any t values greater than or equal to 1. The reason why I chose 1, 4, 9, and 16 is because I'm going to have to square root t. So I just chose values that would be the easiest to square root. And you could keep going, you could use 25 and so on. So when you plug them in, you get 0, 1, 1.3862, 2.197, 3, and then 2.773, 4. So then I'm going to graph these, and then I'm going to indicate with arrows. And then I'm going to solve for t in one of the equations. I chose the x equals the natural log of t. Exponentiate both sides, so t equals e to the x. Plug it in to your other function, y equals the square root of e to the x, and which is the same thing as y equals e to the x over 2. All right, for our third one, we have x equals t squared and y equals t cubed. When you don't have an interval, you will need to find the domain and range of each parametric equation. So for t in both, we have t squared and t cubed, which are both polynomial functions, and both have a domain and a range of all real numbers. So that means in both, t is going to exist in all real numbers. Same with y. But x, in this case, is greater than or equal to 0 because in t squared, you have a parabola where the graph starts at 0 and goes up. So I'm going to go ahead and pick t values, any ones that I want. I just chose my typical -2, -1, 0, 1, and 2. Plug those in to get 4, -8, 1, -1, 0, 0, 1, 1, and 4, 8. Now I'm going to go ahead and graph these points to get a curve that looks like this. And then I'm going to indicate the particle direction with arrows. And then I'm going to go ahead and solve for t in one of these functions. And I went ahead and chose x equals t squared. Solve for t, so t equals x to the 1/2, or the square root of x. Plug that into t in the y equals t cubed, and simplify to get y equals x to the 3/2. All right, last example. X equals sine of t, y equals sine squared t minus 1. And for both of these, t exists in all real numbers because sine has a domain of all real numbers. And we know that sine is between -1 and 1. So therefore, x is between -1 and 1. And y is going to be between -1 to 0 because of this extra -1 right here. All right, so I'm going to choose t values that are in the all real numbers, typically the 0 to 2 pi. Evaluate, so I get 0, -1, 1, comma 0, 0, comma -1, -1, comma 0, and 0, comma -1. I'm going to go ahead and plot these values and indicate with arrows the direction of my particle. So since t is periodic, the particle moves back and forth infinitely many of times along the curve. So that's what these arrows are meaning, is that it's starting at 0, -1, and it's going up, turns around, comes back, just kind of almost like your up-down movement, like a swing. So since x equals sine of t, and I have a sine of t in my y equals sine squared of t minus 1, I can just replace sine of t with x and not even have to solve for t. So I get that y equals x squared minus 1. All right, now let's look at a problem where you have to match the parametric equations, x equals f of t and y equals g of t, in A through D, so these ones, with the parametric curves labeled 1 through 4 over here. So you're matching the pink with the blue. Then you need to give reasons for your choices. And here's a little hint to help you. Use the range of each parametric equation to help you identify the parametric curve. So what I mean by this hint is if we were to look at A, right, and this is the x values. So if we look here, the x values are between 1 and 2. So if I come over here and I look at only my x values, which graph or graphs have x values only between 1 and 2? And as I look at them, the only one that has x values between 1 and 2 is 3. Now I just want to confirm that with the range for the y. And the range for the y is between -1 and 1. So if we look at graph 3, you'll see that the y values are between -1 and 1. So that means A is number 3. All right, so go ahead and see if you can match the other 3 to their appropriate parametric equations. All right, let's see how you did. So we already did A. Now for choice B, you should have chosen 1 because the values of x cycle between -2 and 2 4 times, and the values of y cycle between -2 and 2 6 times. For C, you should have chosen 4 because x is between -2 and 2, and y is between 0 and 2. And then answer choice D should have been 2 because the values of x cycle between -2 and 2 2 times, and the values of y cycle between -2 and 2 also 2 times. All right, well, I hope you enjoyed getting your first dose of parametric equations, and I will see you in class tomorrow. Have a good night.